Okay, so last time we spoke about frequency of the wireless signal. And today we will talk a little bit about modulation and its properties for wireless signal transmission. So, we have this paint, and I'll draw you some properties of wireless signals. So the first property that we talked about was center frequency. We will call it F0, center frequency, which is the frequency at which you are transmitting your wireless signal. Something like that. So it is the frequency at which you are transmitting your signal, and you have to respect the local laws, and you can only transmit at frequencies that are allowed in your territory. There are some countries where rules are very loose. You can transmit in many frequencies. In Europe, you can transmit only in a few bands, like 433 megahertz or 868 megahertz or 2.4 gigahertz, but not in others, because others are used for airplanes, for military, and you should not transmit in the same frequency where airplanes are communicating, because then you can accidentally interrupt their communication and the plane can crash down, for example. So it is forbidden, and it's also unsafe. When you are flying an airplane, you don't really want somebody to interfere with the airplane's communications, right? So don't do it for others as well. So what happens if you transmit at a forbidden frequency? If the signal is low, it's quiet, and it only flies a couple of meters, well, nobody really notices anything. But if you are transmitting it in a loud manner, for example, maybe 100 milliwatts, maybe 1 watt and louder, then, and also you are in the city, then most probably the military forces will detect that there is some data transmission in the forbidden band, and they will locate it using a locational directional antennas, and they will find you, they will track you down, and they will break into your house and find the device, and they will arrest you, and maybe you will face some financial consequences like a fine, maybe you will go to prison. I'm not really sure, but generally military guys and also people from aviation field, they have equipment that can detect the direction of a signal, and they will just track you down and give you a fine. So I don't recommend doing that. Yes. So there will be a penalty if they find you. And actually, I know one case where it actually happened in Latvia. Somebody was transmitting in the forbidden frequency, but I think they did it on purpose. It was some kind of an experiment, but that engineer person did this like a joke, but the device was found, and I think he faced some fine or something like that. He didn't go to jail, but he had to pay some money as a fine. So, I don't recommend it. Anyway, so center frequencies, I'll just write some examples. So European Union, it is 868, 433, 868, and 2.4 gigahertz. So this is megahertz. Okay. Next, so I will draw a picture, which is pretty common when we study about radio frequencies, and it is this picture. So we have frequency on x-axis and power on the y-axis. So frequency, let's say it will be in megahertz, and power, for example, milliwatts, because we don't really use that much energy when we transmit in wireless sensor networks. So you would think that, let's say you pick some frequency, 868 megahertz, and you want to transmit in that frequency. Or for example, 868.3 megahertz. Why it's 0.3, I'll explain a little bit later. But the thing is, you could, for example, transmit at 868.3 megahertz, but the problem is if you just transmit a signal, well, that signal doesn't really transmit any information. You're just pushing a signal into the air. So what you need to do is you need to do some kind of modulation or encoding such that the signal changes depending on the information that you want to send. For example, in the simplest way, you could use, for example, amplitude modulation, or better name is amplitude shift keying. When you want to send 1, it means there is a signal. And if you want to send 0, you don't send the signal. So if you want to send 0, no signal. The problem, this is a very simple thing. So you want to send, for example, 1 0 1 0 1 1 0 1. In that case, you send the signal for a short moment, then you don't send the signal for the same amount of time. Then you send the signal, then you don't send, you keep it quiet. Then you send the signal and send it, again. And then 2 times you keep quiet. And you have sent this 1 0 1 0 1 1 0 0. But the problem with this method is that when you don't send the signal, the receiver doesn't know if this was the end of the message or that this silence is actually more zeros at the end, right? So amplitude shift keying only works for fixed length messages, and it always has to start with 1, so that the receiver hears that, oh, there's a 1, so that this is the beginning of some message, and it needs to count the number of bits, and it has to be fixed. And amplitude shift keying isn't really used anymore. However, it is still in real life for legacy systems. For example, many car remotes use this simple amplitude shift keying modulation to lock and unlock the door. Actually, my friend copied his car's key by simply recording the signal stream that went from his remote to the car, which corresponded to unlocking. So he could actually copy his own car keys. And his car was actually only, it wasn't really that old. It is 1999 Audi A3. So if we go on the internet, 1999, I think it was this. So you actually see a lot of such cars on the street, and it seems, in some sense crazy that these cars use a very simple unlocking mechanism where they just send a constant one signal, no signal stream to lock and unlock the car. So somebody can record this ones and zeros and play them back once more with a very simple, very cheap modulator and unlock your car. Well, the good thing is that cars also have other protection systems like a key, immobilizer. So yeah, maybe somebody can copy the signal, but they can only unlock the door and maybe steal something from your trunk or from inside of the car. So they can't really steal the car that way. But the mechanism is pretty simple. So this signal is used, but it's being obsolete, right? So we have questions in chat. Is it like using this SDR sharp software where it captures the signal and play it again? So my friend used SDR sharp software. That's true. I don't think that he could play it back, but he could record the signal using SDR sharp software. And then he bought a very simple transmitter with on-off switch, and he just turned it on and off in the corresponding times, thus simulating or imitating the same signal that was sent from his car remote. But yeah, I think he used this SDR sharp software. So a much more popular method of modulation is frequency shift keying. So in frequency shift keying, the method is the following. If you want to send a 1, you send it not in the center frequency, but a little bit higher frequency. And if you want to send 0, you send it at a little bit lower frequency. And actually, you never send the signal in the center frequency. You only send it a little bit lower or a little bit higher. And so a little bit higher means, for example, 1, and a little bit lower frequency means 0. And this way, if there's no signal, it means that there's no message. And if you want to send a message that starts with 0, you can do it. You just send a signal at a little bit lower frequency. So for example, if I want to send 0, 0, 1, 0, it means I send 2 times signal at 0, and then I move the transmitter to this higher frequency and transmit 1 for that moment, and then I move it back to 0. And when I have finished, I just switch the transmitter off completely, and the receiver knows that there's no signal, so the message has ended. So this is a much better way to send information. So we will now introduce 2 new things. One will be called delta F, which is the deviation. I will copy the delta symbol from the internet right here. Delta F, deviation. And I will draw it in this picture. Let's see. Delta F is this distance from the center frequency to one side, and from the center frequency to the other side is the second delta F. So there are 2 delta F. 1 and 0 is 2 delta Fs apart, not just 1, okay? And I will just give you an example. For example, in wireless sensor networks, deviation delta F is, for example, I don't know, 25 kilohertz. So in this case, it is approximately a few percent of the entire frequency. So 1 second. share screen. Okay, so one delta F and the second delta F deviation. And I wanted to give you an example. So for wireless sensor networks, it could be, for example, 25 kilohertz. And let's look at, you know, as an example. This is example. Don't think that all wireless networks have exactly 25 kilohertz deviation. It can be, for example, 10 kilohertz, 25, 50 kilohertz, 100, and so on. For example, in Bluetooth, deviation is 125 kilohertz for Bluetooth, so a little bit higher. Let's look at what percentage is the deviation compared to the center frequency. So center frequency is 868, for example, 868.3 megahertz. And okay, so 25 kilohertz divided by 868.3, so it's 300 kilohertz times 100. So deviation is 0.003% of the center frequency. This is why these are called narrow band signals, because the deviation is, compared to the center frequency, the deviation is really, really, really small. So looking from the distance, you know, it looks almost like one frequency. So the deviation is really small compared to the center frequency. So this is why they're called narrow band signals. I will write in a text, Bluetooth deviation is 125 kilohertz. Newest versions of Bluetooth actually use a little bit more advanced modulation. So a Bluetooth version, I think 2 and 3 has this 125 kilohertz, and the newest versions, I think they are using a different modulation, but it has similar properties. Let's see. And the third thing that we can decide for our signal is the speed at which we change from ones to zeros and from zeros to ones. It is called bitrate, and we will describe it with a capital letters BR, bitrate. How many bits per second or kilobits per second? Mostly the signals are sent in amounts of kilobits per second, so I just write it as kilobits per second. In wireless networks that are used today in, for example, smart home or smart agriculture, the bitrate is low to achieve higher range. So bitrate is, for example, for KNX protocol, it is 32.768 kilohertz. For Bluetooth, it is 1 megabit per second, so 1000. Oh, instead of this, it should be kilobits per second. So Bluetooth is optimized for speed, so it has high bitrate, 1 megabit per second. The newest versions of Bluetooth even have 2 megabits per second speed, so Bluetooth is fast. And Other networks like Z-Wave, they can, for example, have a bitrate of 50 kilobits per second or 14 kilobits per second, something like that. And how to choose the bitrate? You know, it's really easy to imagine, let's say, from the receiver point of view, if you are far away from the transmitter, it's easier to receive the signal if each of these bits is sent for a longer time. So you send 1 for a long time, only then you switch to 0, you send 0 for a long time, you send data slowly so that far away receiver understands and distinguishes better ones from zeros. So lower bitrate means higher range. However, in Bluetooth case, Bluetooth was never made as a protocol for high range. It was meant to be used for wireless computer peripherals, which are located maybe 1 meter from computer. For example, Bluetooth speakers, they are located next to the cell phone or next to the computer, so you don't need high range. You don't want your neighbor which is 2 blocks away, living maybe, that he hears your music. You only want that the music is inside your house, so the Bluetooth signal doesn't travel very fast. So they set the bitrate very high because they didn't need much of the distance. Also, wireless Bluetooth mouse, it's not located next to the computer, so you don't need it to be long range. So high bitrate means short range, and the slow signal, low bitrate means longer range. This is why, for example, Wi-Fi sends a signal at, I think, megabits per second, even hundreds of megabits per second, and this is why Wi-Fi range is not very big. It only travels through maybe 2 or 3 walls until it is not receivable anymore. But these wireless sensor networks, they can travel several kilometers of distance. So, you know, you can decide what is your application and then you make the decision about bitrate. And also, bitrate and deviation are connected in a special manner, but I guess it will be better to describe it a little bit later. So when you send the signal, you send it at 2 peaks of frequency, but because you are moving between these peaks at the speed of bitrate, they are actually not thin, they are wide peaks in your radio spectrum, and the width of each side is approximately equal to bitrate. So this, the width is bitrate. Okay, so deviation is here and the bitrate is there. That is the bitrate. So as you can see, Bluetooth deviation, the distance between peaks, is 125 kilohertz, but the width of the signal is 1 megahertz. This can be translated to megahertz into this frequency picture. So these kilobits are the same as kilohertz and megabits are the same as megahertz in our case. So Bluetooth signal would actually look something like this. These peaks are very close together, so the width of the Bluetooth signal is approximately equal to the bitrate. But in more general sense, it looks like the picture that I draw here. So 2 peaks for zeros and for ones. And usually people try to make sure that ones and zeros are in the same count, but that's a different topic. So now we need to talk about the transmitted signal width, which we'll call Tx bandwidth. We want to know how wide is our signal. So if I ask you how wide is our signal in, for example, megahertz, well, it's actually pretty easy. The centers of the signal are 2 times delta f away. So the distance between peaks is 2 times delta f, and the width of each side outside of this range is 1/2 of bitrate. So Tx bandwidth is actually 2 times delta f plus 2 times 1/2 of bitrate, right? Because 1/2 is to one side, then is delta f, then the second delta f, and 1/2 of the other half of bitrate. So it's actually 2 delta f plus bitrate for frequency shift keying signals. And so when I initially told you that the permitted frequencies in the frequency band are 433, 868, and 2.4 gigahertz, the answer is actually only partly correct, because our signal isn't infinitely narrow. It actually is wider. So actually these bands are defined as a range between which you need to be located. So for example, instead of 868 megahertz band, it actually is 868.0 to 868.6 megahertz. So so actually you can transmit in this range in European Union from 868 to 868.6 megahertz. So you need to make sure that the entire width of your signal does not go outside of this band. So actually you cannot send at exactly 868 megahertz, because then half of your signal will be in the forbidden zone. This is why most people just choose the middle of this 868.0 to 868.6 megahertz band, which is 868.3. So if you're in middle, you're the most further away from the permissible sides, so you don't care. You just need to make sure that the deviation times 2 plus bitrate is not wider than 0.6, or 0.6, like this. Okay, so we talked about center frequency, deviation, bitrate, and the total width of our signal, which cannot go outside of the permissible band. And I will just write also the 2.4 gigahertz band is actually in European Union. In most locations, it is 2.400 to 2.485 megahertz. So actually you can transmit the signal within these limits. And at this point, we can also talk about interference. Well, let's say that we have several wireless systems working nearby, and all of them have chosen to use 868.3 megahertz as their center frequency, so the signals overlap, right? So when two devices send at the same time at the same center frequency with similar deviation and bitrate, actually deviation, bitrate doesn't even matter. Uh, the two signals interfere with each other, and usually they just destroy one another. The result is just wrong stream of ones and zeros or something similar. So this is why the regulation also says that you cannot transmit more than 1% of the time, and the longest message, for example, for 868 megahertz, is something like 0.36 seconds. So you send a short message, and then you have to be silent for 99% of the time so that other systems, other devices can also communicate. And you can find this information on the internet, but there's a very good document compiled by Texas Instruments yeah, I guess it's this one, where they have kind of summarized the rules in this one document. So they go through the allowed power and also frequency bands. For example, European Union, where is it? So here's frequency bands for non-specific short-range devices in Europe. Actually, there are multiple bands, and each of them has its own limit. So let's see. For example, 868 to 868.6 megahertz, you can send the signal with power plus 14 dBm, which is 25 milliwatts, but you can talk no more than 1% of the time. Channel bandwidth has no limits, it just has to be within this frequency, this TX bandwidth, okay? So, and for example, this 868 megahertz band is pretty crowded because everybody wants to use it. So there is a second band, 868.7 to 869.2, which you can also use to send signal at plus 14 dBm. But here the rule is that you only can send 0.1% of the time, and 99.9% of the time you have to be silent. So this band is better because it's more silent, but it's worse because you can send less information over it. So for example, you can make a device that transmits the temperature only once a day, or maybe some energy consumption of the day only once a day, and you can use this band. It will be more silent, and more data will go through. And there are other bands which are for some specific reasons, but there are other rules in those bands. And here you have, for example, 2.4 gigahertz band. You can set to avoid interference with Wi-Fi and Bluetooth. You can make your own proprietary communication method, but it has to be more silent. It has to be only 7.85 dBm. So, you can choose the frequency and just configure your settings such a way that it doesn't go outside of the system. And here's another table which is for specific applications. So for example, if you want to make fire alarm system, you can use, for example, this band, but the limitation is that you have to only transmit at +10 instead of +14, and the duty cycle is only 0.1%, and the total bandwidth only 25 kilohertz, and so on. So this document is really good for for a reference, and I think it's pretty up to date. So you can use this document. You go to Google, you type TI, which stands for Texas Instruments. It's a silicon manufacturer, silicon chip manufacturer. Texas Instruments ISM band, and there will be this PDF, and there you will find a lot of information about permitted bands. Okay, so as we spoke, 868.3 megahertz is the center frequency. Several devices are sending at the same time. The signal is damaged. This is why, for example, in 2.4 gigahertz band, in the frequency spectrum domain, you have 2.400 here, and you have, for example, 2.485 on the opposite end. So as you can see, Bluetooth bandwidth is only 0.001 gigahertz, and as a result, in this band you can fit 85, well actually 84 Bluetooth signals, because each one of them is only 0.001 gigahertz. So Bluetooth uses frequency hopping, and it has 85 channels side by side in this band. And as a result, if one Bluetooth device sends at certain frequency, other Bluetooth devices hear it, and they choose a different frequency to communicate. And actually, to be even more robust, Bluetooth devices randomly jump through these frequencies during communication, so that it's very low probability that two Bluetooth devices would jump to the same channel at the same time, and there would be collision. And even if that happens, they have a mechanism where they listen, they hear that somebody else is also talking at the same channel, and they just jump to a different channel. So that method is called frequency hopping. It is implemented in Bluetooth. So for example, in this 2.4 gigahertz band, you have Wi-Fi, Bluetooth, and also microwave ovens. So there's a probability that somebody else is going to be talking in a certain channel. So Bluetooth devices just jump through the channels at high speed, looking for free channels and sending information over those. In 868.3 megahertz, you can only have probably maybe 4 or 6 channels, but at 2.4 gigahertz you can have, for example, 85 channels, each at 1 megahertz wide, so high speed transmission, low interference. So that is all about sending the signals. You pick center frequency, deviation, bitrate, and you just send the signal. And so that is about the transmitter, and we can also actually try to look at how the transmitter is built in the simplest form. So I was talking about transmitting the signals, but how exactly is a transmitter built? So transmitter is a device that generally just consists of a generator. Maybe I'll draw it with freehand. we have a signal generator. We generate signal at, let's start with the center frequency. So let's say at 868.3 megahertz. It just generates signal. And it is connected to an antenna. In the simplest form, it will be connected to a dipole antenna. So at high frequencies, rods of metal turn into antennas and they start to transmit a signal. We will talk about antennas a little bit later, but for now, so basically what we have is these two rods. They have mutual inductance and capacitance, and they start to resonate at this frequency 868.3 megahertz, and you can transmit the signal into the air. So if you wanted to do a simple on-off keying or amplitude shift keying or amplitude modulation, you would just put a simple switch here and like this switch. So if you turn on the switch, the signal is being transmitted, and if you disconnect the switch, the signal is stopped. So, you know, it's like an old telegraph where you would just send Morse code pushing a button. So you want to send, for example, 10101100. It would mean that you hold the button down to send 1, release it to send 0, hold down to send 1, release to send 0, then hold down 2 times to send 2 ones, and then send 2 zeros by releasing it. And you can take an Arduino microcontroller and connect one of its pins. Instead of switch, you can use either a relay or just a transistor, and you can send this signal using microcontroller. You can, for example, program it to send a certain string of ones and zeros once a day, for example, and it will just do it. And you can find such transmitters, and you can actually buy them. You know, AM transmitter. Let's see. Let's see. So you can actually buy such things. Oh yeah, this one. I think that my friend that had his car used this thing. So it just consists of resonating circuit with some high frequency generator. You connect it to antenna, and if you give it power supply, it will turn on and transmit. And if you disconnect the power supply, it stops transmitting. So this way you could make a very, very primitive amplitude shifting modulator. So, and this is done in the car remotes, actually. Very, very simple schematic. This is why car remotes should actually be pretty cheap. They aren't because they're exclusive, but you know. So right now we want to upgrade our system so that instead of this stupid on-off keying, we use something more advanced like frequency shift keying. So what we can do is we can have 2 generators. One will be at 806, let's say we have 25 kilohertz deviation. So one will be at 868.325 megahertz, and the other one will be at 868.275 megahertz. And we connect the grounds together, for example, but we just switch over between off state, where the antenna is disconnected from the generators. Second state is we send 1 by connecting this switch to the first generator, and we switch to 0, transmitting 0, by turning this knob to position 3, which will connect it to the lower frequency generator, and we will be sending zeros. So again, instead of this switch, you can put a circuit with transistors or relays if you want to, and you can just switch between off, which is no signal, no information being sent, and then switching between sending ones and sending zeros. With a simple switch, you can do it with hand, you can program Arduino microcontroller to do it. So this would be a second option, but as you know, and actually some first devices were probably built this way, but you see that you have two oscillators which are actually at a very similar frequencies. So is it possible to maybe somehow use one oscillator to do both things? And fortunately it is possible. It is possible because people have invented an oscillator which you can control with voltage. It's called voltage controlled oscillator. And there are many ways to implement it. For example, here it is low frequency with operational amplifiers. At high frequency, I think that they use a diode which is reversely biased, and it changes its capacitance based on the voltage applied. So you apply high voltage, its capacitance goes down and starts to oscillate faster. And if you reduce the voltage, the capacitance goes up, it starts to oscillate slower, and it is fed into an amplifier and transmitted in the air. So instead of doing this, we will use a voltage controlled oscillator, VCO, voltage controlled oscillator. And we will still have on off switch to switch the oscillator off when we don't want to send any data. But generally, voltage controlled oscillator has an input, and it is configured in such a way that if we set input to 1, it starts to oscillate faster and sends signal at higher frequency. And if we change the input to 0, it starts to oscillate slower and sends frequency at lower, sends signal at lower frequency. So you can buy these things, or in the labs, in our development kits, the radio frequency chip has this thing built in. So we are using, for example, SX1276, I think. Data sheet, here it is. This is low resolution. So here is a oscillator which you can control with voltage. High band frequency fractional PLL. I think this is the oscillator. I don't know. Maybe there is a better picture, but generally that's the transmitter part. So if we want to send a signal high band fractional PLL, radio frequency out, high frequency. So I guess this is the part that is being, that is the transmitter. Okay, so you can buy them, you can probably build them, but these radio frequency chips have them built in. And this way you can change the frequency and you can send it faster or slower. Okay, but one thing that you need to understand is that generating 868 megahertz is actually a very complicated task. It's not really that easy, and you cannot really make a mechanical, some kind of circuit that would oscillate at these speeds and be stable. So actually, in reality, the contents of the transmitter are the following. You have a transmitter, TX, and it actually doesn't really have 868 megahertz input, but it has a connection for external lower frequency crystal, and inside of it, it has a block called PLL, phase locked loop, which is able to upscale or multiply the incoming frequency to higher frequency. So we can buy a crystal that is an electromechanical component, which when bent generates a small voltage, and you can use it to bend it to the opposite side, and then it produces the opposite voltage, and basically you can make an oscillator out of this quartz crystal. And quartz crystal has a fixed resonating perfect frequency, for example 30 megahertz, right? It is approximately 30 times less than we need, but these can be manufactured and built. Well, let's see, for example, we go to a crystal manufacturer. Quartz crystals and oscillators, quartz crystals. What is the fastest crystal that this particular manufacturer can build? Frequency in megahertz. We scroll down to the bottom, and the highest frequency that can be built mechanically for this particular case is just 50 megahertz, but we need 868 megahertz. So because these crystals at 800 megahertz cannot be built, so we take a crystal with lower frequency, and then there is a very smart way to upscale, to multiply this frequency to get the frequency that we need. And this is done by this PLL block. So we feed the lower frequency, PLL multiplier multiplies our signal, and we can actually calculate by how much it multiplies the signal. So let's say we need 868.3 megahertz. We divide it by our reference crystal, which is 30 megahertz. And actually the multiplier is 28.94. So this PLL, it's fractional PLL, so it can actually multiply with some fractions, not all, but some. So it multiplies the signal by 28.94, and the resulting signal is sent to the antenna. But, well, to be perfectly precise, there is another block which manipulates the frequency also a little bit, you know, to change from ones to zeros and back. So there will be some kind of voltage controlled oscillator. So PLL generates the center frequency, and then voltage controlled oscillator shifts a little bit higher or lower. Okay, so why is it important? Why am I telling you this? I'm telling you this for the following reason, which you need to kind of, you know, understand. to be successful at constructing the wireless networks. So we know that the transmitted radio signal is generated by multiplying crystal frequency with some multiplier, for example, 28.94. So the question is, how precise will be our output signal? In a sense, how stable it is. And the problem is that these crystals that we have here, they have three causes of not being exactly precise. So first is precision from manufacturing side, point of view. So you make 1,000 crystals, each is supposed to be 30 megahertz, but you know, nothing is perfect, nothing is equal. So of course, one crystal will be a little bit worse at a little bit lower frequency, for example, 29.99 megahertz, and the other crystal will be 30.001. So they have some kind of precision expressed in parts per million. Another thing is, if you, so how the crystal is made up, it consists of quartz, piece of quartz, which is cut with a laser to a certain length, so that this length produces the resonating frequency. So it is kind of electromechanical thing. And the longer the piece, the slower it oscillates, just like a ruler. You know, you have a ruler on your table. If you set it at a long distance from the table, it oscillates slowly, but if you leave a shorter piece over the table, then it will oscillate faster. So if this piece, this crystal, gets hotter, this piece gets longer and it starts to oscillate more slowly. And if you put it in cold, it shrinks and it starts to oscillate faster because it's shorter, it can move faster. Well, actually, the process is more complicated, and the oscillation deviation has a little bit different form, but generally, temperature impacts the precision of the crystal that is used for transmission. So one is precision, and the second is temperature. It's expressed by parts per million over the entire temperature range. So we have precision, we have temperature, and the third bad thing is aging. So you build your device, and it happens so that after manufacturing, this crystal actually keeps transforming a little bit. For example, you solder it to a PCB, but when you put the PCB inside the final plastic case, the PCB is bent a little bit. It's under a little bit of mechanical stress. This crystal, if it happens to be in that location, it feels it, and it stretches or compresses a little bit, and its frequency also changes. So it changes, but then it stops changing. So it is measured that after something like 2 or 3 years, the crystal has changed its frequency by several ppm because of aging. After that time, the stress has stopped, or the stress has reached its equilibrium. So aging slows down after a couple of years and doesn't really change anymore, but it also changes this frequency a little bit. And if you add all of these three things together, it turns out that the output frequency can change by several percent. So let's check out. For example, this manufacturer produces crystals at frequency 30 megahertz. And as you can see, having 30 megahertz, you have several options. You can choose a crystal with precision 50 parts per million, or 10, or 15, or 20, and you will probably guess correctly that the better the tolerance, the more expensive the part costs. You know, it's easy to produce a part with 50 ppm, but it's really hard to build a part with only 10 ppm precision. And there is this theory that they actually build all of these parts the same, and then they measure, and then they only pick those that are within 10 ppm in one box and sell them as plus minus 10 ppm parts, and the others that are further away from the center, they sell as 50 ppm parts. I don't know if it's true, but there is this rumor. And the second is stability. This is the temperature stability. And again, you know, one piece deviates a lot based on temperature, and another part deviates only a little bit. So this is 50 ppm and this is 10 ppm. So, you know, more precise part will be more expensive. And you can also see the operating temperature. So in general, all of these crystals would work up to their melting temperature and down to absolute zero. It's just that these properties, tolerance and stability, are only guaranteed between this given temperature range. For example, for this cheap part, which is not very precise and not very stable, these properties are within minus 10 to plus 60 degrees Celsius. If you put this part in plus 70 degrees Celsius, it will work, but the stability and tolerance will be even more off. Maybe it will be plus minus 70 or 80 parts per million off. So it's just the more precise and higher temperature range, the more expensive the piece is. So which is the best part that we can find? At 30 megahertz, probably this one. It has plus minus 10 ppm, plus minus 15 ppm due to temperature, and the temperature range from minus 40 to plus 85. So it's very precise. High temperature stability over wide temperature range, right? So what exactly does it mean? So let's take, for example, this crystal at 30 megahertz. Its precision is 50 ppm. Stability over temperature range is also 50 ppm. You have to remember that these are not absolute numbers. To get kilohertz or hertz of precision, you need to multiply parts per million with the millions of hertz. So actually, it's not, you know, 50 parts in a million. It's actually 30 megahertz times 50 parts per million is 1500 hertz deviation. So let's put these numbers on paper. Let's say that our transmitter is 30 megahertz, but plus minus 50 parts per million precision and 50 parts per million maximum offset due to the temperature. So what would be the slowest case for this crystal? So instead of 30 megahertz, we need to subtract 50 parts per million due to the imprecision of manufacturing, and another 50 parts per million due to the temperature. For example, we put it at minus 10 degrees. So the temperature, the frequency goes, for example, down, or maybe it would be easier to say that at high temperature, frequency goes down, but that wouldn't be correct either. So, so 30 times 50 equals 1,500 hertz equals 1.5 kilohertz, which is the offset from the center frequency because of manufacturing. And let's say we put it at high temperature, this crystal expands, becomes longer, and starts to oscillate slower, and the manufacturer says it's no more than 50 ppm. So let's take worst case scenario, 30 megahertz times 50 parts per million from temperature is also 1,500 hertz is 1.5 kilohertz. Temperature caused offset. So, and we need to add them together. So the total offset is 3 kilohertz. So actually, at low temperature, at highest temperature, and in case we pick the worst case crystal, its actual frequency is not 30 megahertz, but 30 megahertz minus 0.0015. Yeah, I think I calculated correctly. Is actually 29.9985. Right. So, is it good or is it bad? It looks small at the moment, but if we use the same multiplier, then we multiply this low frequency with the PLL, and only then we transmit this frequency to the air. So in the air, let's say our multiplier was 28.94. So now when we multiply 29.9985 times 28.94, we get 29.90, no, 28, yeah. So 29.9985 times, oops, 29.9985 times 28.94, instead of 868.3, we only get 868.16, which actually is pretty much off of what we expected initially. So it is 868.15659. So because of the crystal precision or lack of precision and temperature impact, the output frequency is actually totally different from what we expected. We wanted it to be 30 megahertz times 28.94. It should have been 868.2. Yeah, okay, the difference isn't that big, but we need to take it into account. So instead of 868.2, we get only 868.16. And if, for example, we have a very small deviation, then the signal looks like it's even maybe on another band instead of the band that we need. And okay, so the difference doesn't look that big yet. So this is our reference. But let's say that, okay, the transmitter is, for example, hot, and we picked accidentally the slowest crystal. So the transmitter is sending at 868.15659 megahertz. The receiver is built similarly. It listens to the signal and it's tuned to the center frequency. It filters out all the sidebands, otherwise it would hear all the possible frequencies in the world and not know which signal is intended for the receiver. So receiver tunes to the same center frequency using a similar, almost same crystal. So receiver, let's say that for receiver, we picked the fastest crystal, which has deviation of plus 50 ppm. It means that it will have 1.5 kilohertz higher frequency than expected. And let's say we put it in cold temperature where this crystal shrinks, for example, outside in the winter, it starts to oscillate faster. And instead of 30 minus 0.0015 receiver, for example, in the worst case scenario, the receiver's oscillator is actually oscillating faster than necessary. 30 plus 0.0015 is 30.0015 megahertz, right? So when receiver multiplies this frequency to this higher frequency, the resulting frequency will be 30.0015 times 28,494 is no. It is 868.24341. Uh, 24341. And as you can see, in the worst case, a transmitter is sending at 868.16 megahertz. But the receiver, because it is in a different environment with a different crystal, actually here listens to a little bit different frequency, 868.24. You know, the total difference is approximately 80 kilohertz, which is actually really big if you think about it. So the difference is this minus 868.15659, and we multiply it by 1000 to get kilohertz. 86.82 kilohertz is the difference in worst case scenario between sender and receiver. And as a result, if, for example, your signal's bandwidth was only 25 kilohertz, the receiver will not hear the transmitter because in frequency domain, transmitter is sending at 868.15659, but the receiver is listening at 868.24341, right? Well, I'll draw it in a different way. So the receiver is listening to this band. It's listening here, but the transmitter has deviated because of crystal imprecisions. And as a result, receiver doesn't hear anything because transmitter is transmitting at a different band outside of receiver's reach. So in radio frequency deals, you need to remember that this crystal needs to be as precise as possible. And as you can see, you should not use this 50 ppm. You should use something like 10 ppm, maybe 15 ppm, and maybe even more precise crystals. So crystal is really important. You can get crystals with precision of, for example, plus and minus 10 ppm. Unfortunately, that is approximately as good as they get. We can go to the specification and check it out, and it has all of the information, and the stability is anyway 15. So the formula to calculate the worst case offset between temperature between crystals is worst case frequency deviation. For example, frequency error is crystal's frequency I'll call frequency of oscillator multiplied by ppm of manufacturing plus ppm of temperature and multiplied by 2 because one crystal can be manufactured at minus 50 ppm and temperature effect can make it become minus 50 ppm. So it's a sum to the negative side, but the receiver can, for example, accidentally happen to be plus 50 ppm precision and plus 50 ppm because of the temperature. So it's 2 times oscillator frequency, for example, 30 megahertz times 1 ppm plus the other ppm, for example, 10 plus 15 or 50 plus 50 as in this case, times 2, because one receiver can deviate forward and transmitter can deviate backward. And this is times the multiplier, times the PLL multiplier. And this will give you the total frequency error, right? So, and basically, a good option is to just have it at approximately 10 ppm. If you need more precision, you can buy thermally compensated crystal oscillators. They are more expensive. Crystals usually cost something like 20 cents, 50 cents, approximately, I don't know, for example, 30, 0. Euros. But if you need more precision, then you need to buy temperature compensated crystal oscillators. I wonder if there is some article about it. And the idea is that in this temperature compensated crystal oscillator, its construction is such that when the crystal expands, there's another piece of metal that expands the same amount and pushes the crystal back together so that the temperature is compensated. or there is some electronics that measures the temperature, and based on the temperature, it changes the crystal's frequency a little bit, right? And with temperature compensated crystal oscillators, let's see, do we see them in this? So temperature compensated. I don't know if these are the correct ones, but temperature compensated crystal oscillators have precision of, for example, PCXO. Precision is, for example, 1 ppm, right? 10 times better. Precision maybe is 2 ppm. The temperature impact is approximately 1 ppm or 2 ppm. So, you know, it's a lot better. It's a lot more precise. But the price is something like €2. So you need to decide, do you really want it to be this precise or not? Some applications require maximum precision, but some applications require maximum cheapness. And there's also something that is called oven crystals. I don't remember their name, but the idea is that the crystal is just artificially heated up to a certain temperature and kept that way. For example, heated up to 300 degrees, and you know, you don't care if it's minus 30 or plus 25. It's kept at constant temperature, so it doesn't change its frequency. Okay, so if you have any questions, you can write them in the chat. Otherwise, that's all for today.